In this next lesson, we're going to have a look specifically at friction on slopes and statics problems. Now, before we start that, I just wanted to focus on what we know already about friction and how it works. So let's make this quite sticky. If I increase the force, so the red force on the right, the friction increases at the same rate until you reach a point where the applied force is larger than the maximum friction, and then it moves off. Okay, this is what we discussed when we were doing chapter 5. So let's do it again. So you can apply a force and it just acts to match it. If I go the other way, then the friction will act the opposite way, and it just acts to stop it. So if I applied 5 newtons, then 5 newtons of friction would stop it. However, there's always an upper limit, which is what we use F equals mu r to calculate. And once you hit that upper limit, you can then start moving off, like that. And then it will accelerate and get faster and faster and faster. So that's what I want to focus on now, but involving slopes as well. Now, if this object here, so I've got a slope of 30 degrees, mu is 0.2, and there's a force pushing the object up the slope. Now, if it's in equilibrium, so that means that overall it is not accelerating up or down, it's just sat there. There's actually two different scenarios that could happen. From the outside, just looking at it, they would look the same. So if you were watching this box, it would just look like the box was still. But actually, there's two different scenarios that could happen. We can be on the point of sliding down the slope, or we can be on the point of sliding up the slope. The way that I normally explain the difference is imagine that you were moving some furniture. Okay, so you've probably been in this scenario before. Maybe you are moving some furniture up some stairs. Okay, if it's on the point of sliding up, this is when you're pushing hard enough to actually make your bit of furniture go up the stairs. That takes quite a lot of effort to get your wardrobe to actually move up the stairs. So here, P is going to be quite big. Here, if it's on the point of sliding down, so it's just about to start moving down, that's basically when you've got your bit of furniture and you're just trying to hold it in place. Maybe your dad or whoever's helping you at the top of the stairs is having a rest and you're underneath it and you're just applying enough force so that it doesn't fall down and squash you. Both scenarios from the outside look the same because the box is not moving, but in this one, P is actually quite small, although at least it's the smaller of the two scenarios anyway, because all you're doing is you're just stopping it sliding down. Whereas in this one, you're trying to actually get it to move off and move up the slope. Okay. Now, let's actually work out what these two values of P could be in these two scenarios. Let's do this one on the left first of all. So we can draw the weight on. So this is going to be 5G. Resolve it as we do normally. So this is going to be 30. Then we've got 5G cos 30. And we've got 5G sine 30. We have also got the normal reaction force, which is perpendicular to the slope. Now the other forces on here is friction. If it is on the point of sliding down, so the object wants to move down, so therefore friction must act upwards. Okay, it wants to slide down, so friction is trying to stop it. Remember, that's what friction tries to do. It tries to slow things down, or it tries to stop them. So friction is going to go up in this case. So what we need to do now is resolve to find R, because then we can find what friction is, and then we can resolve parallel to the slope. So perpendicular to the slope, R must be equal to 5G cos 30. And now we can resolve, I'm going to resolve down the slope, just because it says on the point of sliding down. So resolving down the slope, we've got 5G sine 30 minus the friction, which is mu r, so it's going to be 0.2 times r, which is 5G cos 30. And then we've got minus p, because p is going up the slope, and that equals 0. because it's not accelerating, it's still in equilibrium. Okay, it's not actually sliding down, it's just on the point of sliding down, so the acceleration is still 0. And we can then solve this to find P. When you calculate that, you get about 16 newtons. So 16 newtons is required to just stop it sliding down the slope. Now let's calculate the other one. Do exactly the same process. So we've got 5g cos 30, 5g sine 30. Just going to draw some arrows on them. Got r. Now if it's on the point of sliding up the slope, so the object is going to move up, friction is trying to stop it, so friction this time acts down the slope. Resolve perpendicular to the slope to find r. And then we can resolve, I'm going to resolve up the slope this time, just because it's on the point of sliding up. So I've got P is going upwards, minus the friction, because that's going down now, so that's mu r, so that's 0.2 times 5g cos 30. And then we've also got minus 5g sine 30, because that's going down the slope as well. And that all equals 0, because the acceleration is still 0. And now I can solve this to find P. And if we calculate that, we get P equals about 33 newtons. So you can see it's more than double the force is required to actually make it move up the slope. And you've probably felt this in real life. Stopping things falling down a slope is a lot easier than it is to actually give it a really big shove and get it to slide up the slope. But there's two different scenarios here. And if you see the wording on the point of sliding down or on the point of sliding up, you need to think carefully about which direction is the friction going. But in general, friction is trying to stop things. So if it's on the point of sliding down, friction must be going up. If it's about to move up, friction must be trying to stop it and pushing down. And that's the main thing that affects how you model this. Let's have a look at another example similar to this one. So this is one of the later questions in the exercise you're about to do, but I thought we would go through this one in particular. So a box of mass 1 kilogram, let's just put that on, is placed on a plane. Let's put the weight on and resolve it straight away. So that's going to be 40 up there. So that's 1g. So this is going to be g cos 40 and g sine 40. In those directions. It's always useful to write the arrows on just so you don't forget which way they're actually going. I suppose we could draw r on at the same time. The box is kept in equilibrium on the point of moving up. So it's in equilibrium on the point of moving up the plane. So if it's on the point of moving up, it wants to accelerate upwards, so the friction must be going downwards, like that. The string makes an angle of 20 degrees with the plane. Okay, so we've got this string with a force of 10, an angle of 20. So let's resolve that whilst we're here. So that component there is going to be 10 sine 20. And this component here is going to be 10 cos 20. Okay, so I think that's all of our forces on there, and they're all resolved. So it's in limiting equilibrium. If it's in limiting equilibrium, then that means that the friction is at its maximum. Okay, so this means the maximum friction is being applied. We've got to find mu. Okay, so we're rather being told it, we've just got to work it out here. But we're still going to follow exactly the same process that we would normally. Let's find out r first of all, because then we can try and calculate the friction. It'll have to be in terms of mu, but that's fine. So if we resolve perpendicular to the plane, so I've got r plus 10 sine 20. Okay, because I need to take this bit here into account as well. That must equal g cos 40. And then we can solve this to find r. when we do that, I suppose you could keep it exact, but I think with things like cos 40 involved, it's fine to just write as a decimal. So r is 4.087. I'll do a few decimal places. And now what we're going to do, it's on the point of moving up, so I'm going to resolve up the plane. So I've now got the force pulling it up the plane is 10 cos 20. The force is trying to stop it. I've got friction, so that's going to be minus mu r. That's minus mu, I don't know what that is, times r. And I've also got minus g sine 40. And that equals ma. Well, it's just going to be 1 times 0, because it's in equilibrium still. And now I can solve this equation to find out what mu is. And when you solve this, you get mu equals about 0.76 or 0.757. Oh no, 758 actually. There we go. So in terms of the calculation, there's not really a lot of algebra calculation going on here. Most of my work is actually on the diagram, and that happens quite a lot in mechanics. Draw a nice large diagram and do all of your working out and thinking on the diagram, and then that makes the actual equation bit and solving quite easy. And this is a 7-mark question in an exam. So you should now be able to have a go at anything in exercise 7c. I've also got my own work solutions to that, which sometimes is a slightly different method to the book, but then it gives you 2 different ways of doing it. Not quite as nice handwriting as the proper work solutions, but it might be helpful.